Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. If you found useful, please don't forget to like, share, comment and subscribe. Your comments are highly valuable to me. Please don't forget to press the bell button to get the notification of next video. The topic for today's discussion is application of Bernoulli's equation. Bernoulli's equation is obtained from the conservation of momentum for a fluid particle moving along a streamline. Based on Newton's law of motion, Bernoulli's equation can be viewed as work done by the action of pressure force and gravity force on the fluid particle that is equal to the increasing kinetic energy of that fluid particle. So despite of highly restrictive approximations used in the derivation of Bernoulli's equation, Bernoulli's equation is commonly used in engineering practice since large number of fluid flow problems can be analyzed with reasonable accuracy by using this equation. So Bernoulli's equation can be applied at the 2 points by equating the energy at the two sections, that is total energy at the section 1 that is equal to total energy at the section 2, and this equation is valid for ideal fluid because we haven't considered the losses that is taking place from section 1 to section 2. So for ideal fluid there is no viscosity, that means there is no loss. Whereas for real fluids, if you are balancing the energy between the two sections, that is total energy at the section 1 equal to total energy at the section 2 plus head loss. So if you are applying this Bernoulli's equation for a horizontal pipe and balance the energy between the two sections. So here these two sections are equidistant from the datum. So Z1 equal to Z2. So we can write this expression as P1 by rho g plus V1 square by 2g, that is equal to P2 by rho g plus V2 square by 2g plus HL. The kinetic equation is valid here. That means so Q equal to A1 V1 equal to A2 V2, or velocity is calculated V equal to Q by A. Consider these pipe segments. So here the flow is taking place from section 1 to section 2. But because of the reduction in the flow area here, for the same discharge, velocity that is get increased at the section 2. If we are neglecting the energy loss between the two sections, then this expression turn into P1 by rho g plus V1 square by 2g, that is equal to P2 by rho g plus V2 square by 2g. So based on this equation, for any change in the cross section, that will change the velocity. So the corresponding change we can observe the pressure here to balance this equation. So if you are comparing the velocity at the section 1 and 2, here the velocity is higher compared to the section 1. Since there is no change in the cross-sectional area at the section 1 and 2, V1 that is equal to V2. So in this figure, that is V2 that is higher than V1. Correspondingly, P2 by rho g get reduced because of the increasing velocity, so that these equations get balanced. So this pressure velocity relationship along with the kinetic equation can be utilized as a principle for the flow measurement techniques. So one of the flow measuring device which is developed based on this principle is Venturimeter. So Venturimeter is a device which is used for the measurement of rate of flow through the pipe. So the basic principle is by reducing the cross-sectional area, a pressure difference is created, and by measuring the pressure difference enables the determination of discharge. So this is the sectional portion of the Venturimeter. So you can see that the main parts of this Venturimeter is a convergent cone followed by a cylindrical throat followed by a divergent cone. So this portion of the Venturimeter that is attached with the pipe. The diameter of this convergent cone is as same as that of the pipe, and degree of convergence that is equal to 21 degree. This cylindrical throat has a length that is equal to the diameter of this throat, and a degree of divergence here that is equal to 5 to 7 degree. So compared to this length of divergent cone, the convergent cone is shorter. So that is because when the flow is approaching this convergent cone, the flow that is getting accelerated, then it is enters to the throat section where the flow area is minimum, then the flow is getting diverged. After the throat, the size of the flow area that is getting increased. So that means flow is getting retarded. because of the increasing cross-sectional area, there is a chance of flow separation. So in order to avoid the flow separation, we are providing enough length for the divergent cone so that the flow is closely follows the boundary. So there is no separation of the flow that is taking place when the flow passes from throat to divergent cone. So that will be increase the efficiency of the flow measurement. Because of the reduction in the flow area, there is a change in pressure that is taking place between the convergent cone and throat. So this pressure difference we have to measure. So we have to utilize this pressure velocity relationship along with the conductivity equation. Then we can develop an equation for the computation of discharge. Now let us apply this Bernoulli's equation at the section 1 and 2. Since this Venturimeter laid horizontal, Z1 equal to Z2, so this equation can be rewritten as P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g. So since we are neglect the losses that is taking place between 1 and 2, so HL also can be eliminated. So P1 by rho g minus P2 by rho g equal to V2 square by 2g minus V1 square by 2g. This difference of pressure is indicated by pressure head, that is represented by H. P1 by rho g minus P2 by rho g, that is equal to H, that is equal to difference in velocity head between the section 1 and 2. Based on the kinetic equation, theoretical discharge equal to A1 V1, that is equal to A2 V2. So A1 is the cross-sectional area at the inlet of the convergent cone, and A2, that is the area available at the throat. And the corresponding velocities are V1 and V2. Since we haven't accounted the losses between the section 1 and 2, the discharge calculated is theoretical discharge. So from this equation, we can replace V1 as Q theoretical by A1 and V2 as Q theoretical by A2. So if we are substituting V1 and V2 in this expression, then we can modify this equation in terms of QTH as QTH equal to A1 A2 into root of 2GH by root of A1 square minus A2 square. You can substitute and verify this equation. So A1 and A2 are the areas at the convergent cone and the throat. H is the difference of pressure head between these two sections. But the actual discharge that is less than the theoretical discharge. So we can relate the actual discharge and theoretical discharge by means of a coefficient that is called coefficient of discharge. So actual discharge equal to coefficient of discharge into theoretical discharge. So the expression for the discharge computation, that is Q equal to CD into A1 A2 into root of 2GH divided by root of A1 square minus A2 square. For a given Venturimeter, A1 and A2 are fixed and CD that will be available with the manufacturers. So if we are fitting the Venturimeter to a piping system where we want to measure the discharge or rate of flow, by measuring the pressure difference between convergent and throat, then we are able to calculate the discharge. That is the advantage. So that can be done by connecting the limbs of the manometer at the convergent section and at the throat. So how to determine pressure difference between the 2 points explained in the next section. So we connected the 2 limbs of the U-tube manometer at the convergent cone and throat. Because of the difference in pressure, the manometric fluid in the U-tube manometer get deflected. So how to convert this deflection into pressure head, that is discussing in the next section. So the difference of pressure between these 2 points can be determined by writing the pressure balance equation. So the principle used for writing this equation is, one is Pascal's law and the other is sign concept. So if we are equating the pressure in the 2 limbs at this level, P1 by rho g plus x into s, where s is the specific gravity of this flowing fluid, that is equal to P2 by rho g plus x into sm, where sm is the specific gravity of the manometric fluid. Rewriting this expression as P1 by rho g minus P2 by rho g, that is h, that is equal to x into sm by s minus 1. So X is the deflection of mercury in the U2 manometer. So by using this equation, we can convert the deflection of mercury into pressure head. So if you are using inverted U2 manometer, the specific gravity of manometric liquid is less than the specific gravity of the flowing fluid. So in that case, H equal to X into 1 minus Sm by S. So by using this concept, we can convert the deflection of mercury into H, and H can be utilized in the discharge equation of the Venturimeter. So if you are erecting this Venturimeter in the inclined position or in the vertical position, there is no change in the equation. Let me explain that by applying this Bernoulli's equation at these two sections. So Z1 and Z2 are the positions of section 1 and 2 with respect to the datum. So this is the Bernoulli's equation at the section 1 and at section 2. So if you are rewriting this expression as P1 by rho g plus Z1 minus P2 by rho g plus Z2, that is equal to V2 square by 2g minus V1 square by 2g. So the difference of piezometric head between the two sections is the pressure head, that is H equal to V2 square by 2g minus V1 square by 2g. So from this we can develop our earlier equation. In the piping system, even if Venturimeter we erected in the inclined manner or in the vertical position, so there is no change in the discharge equation. Another device which is developed based on the principle of Bernoulli's equation combined with kinetic equation is Orificemeter. It is also called orifice plate. Compared to Venturimeter, orifice plate is much cheaper, so and it is commonly used. So orifice plate, it is a circular plate which has a hole at the center. So this orifice plate installed between the pipe segments. So these are the two pipe segments. In between we are installing this orifice plate by using flanges. Outer diameter of this plate is as same as that of this diameter of the pipe. So when the flow that is approaching this orifice plate getting contracted, then after passing through this orifice it is getting expanded. So because of this flow reduction in area, there is a pressure difference that is taking place. So that pressure difference can be measured by using pressure gauges, and that pressure difference we can relate with the discharge. So this figure represents the flow pattern that occurs when we install an orifice plate. Approaching flow that is getting accelerated towards this orifice and that is getting expanded further when the flow area that is getting increases. So during the deceleration of the flow, there is a separation of the flow that is taking place from the boundaries. So large amount of eddies that will be there in the separated area, so that will induce large amount of losses. So because of this flow separation, flow area that is also getting reduced, so compared to the orifice area. So area A1 represents the area of this pipe and area A0 which represents the area of this orifice. So this area that is the contracted portion, the smallest flow area called vena contracta. Area at the vena contracta that is equal to A2. Now we can apply the Bernoulli's equation at the section 1 and 2. This alignment is horizontal, we can eliminate Z1 and Z2, and we are not considering the losses that is taking place between the section 1 and 2. So this equation is now rewritten as P1 by rho g plus Z1 minus P2 by rho g plus Z2, that is equal to V2 square by 2g minus V1 square by 2g. The difference of piezometric head is indicated by H, that is equal to V2 square by 2g minus V1 square by 2g. So V2 can be expressed as V2 equal to 2gh plus V1 square raised to half. Now based on the continuity equation, A1 V1 that is equal to A2 V2. So V2 is the velocity at this flow area. So this is a theoretical velocity. Actual velocity at this area can be calculated by introducing a coefficient that is called the coefficient of velocity. So this V2 now can be written as the coefficient of velocity into V2. CV is called coefficient of velocity. Now based on the continuity equation, we can write A1 V1 that is equal to A2 V2. Area here, that is the smallest flow area, which is less than the orifice area. So orifice area is available with us. So we can relate this area A2 with respect to that of A0 by means of a coefficient that is called coefficient of contraction. So A2 can be written as Cc into A0. So from the content equation, we can write V1 that is equal to A2 V2 by A1. Now A2 is replaced by Cc into A0, where Cc is the coefficient of contraction. Now if you are substituting the value of V1 as Cc into A0 by A1 into V2, then V2 can be written as V2 equal to Cv into 2gh by 1 minus Cv square Cc square into A0 square by A1 square raised to half. But based on the content equation, discharge equal to A1 V1 equal to A2 V2. So A2 is replaced by Cc into A0 into V2. Now V2 is replaced by this expression. So Q can be written as Q equal to Cc into A0 into replacement of V2 by means of this expression. Cc is coefficient of contraction and Cv is coefficient of velocity. So the product of Cc into Cv is indicated by coefficient of discharge. So this equation is now modified into Q equal to Cd into, Cd means the product of Cc into Cv, that is Cd into A0 into, then here also we replaced Cv square Cc square by means of Cd square. So this equation is now turned into in this form. Next step is the conversion of this equation similar to the discharge equation of Venturimeter. So by converting it, we can express this equation as Q equal to a constant into A1 A0 into root of 2gh divided by root of A1 square minus A0 square. So A1 is the pipe cross-section area, A0 is the area of the orifice, and H is the pressure difference between these 2 points, and C is the constant which is expressed in this form. So by noting this equation, we can see that for a orifice plate is concerned, A1 is fixed, or outer diameter of the orifice plate is fixed, and A0 that is also fixed. C is the expression that is calculated based on this constant, so that is also available. So the only measurement we have to do to calculate flow rate that is passing through the pipe is the measurement of the pressure difference between these 2 points. So that can be done by using pressure gauges or by means of U-tube manometer. So for the better performance of orifice plate, keep this A0 by A1 ratio as 0.5. So these 2 devices can be used very effectively for the measurement of the flow rate that is passing through the industrial pipe systems. Because of the flow suppression, compared to the Venturimeter, the losses taking place in the orifice plate is more. Now the session comes to an end. For the time being it is enough. Thank you. Please don't forget to press the bell button to get the notification of next video.